Happy to invite the next speaker who hasn't been around for quite a quarter of a century, but close to it. It's almost 20 years now. Professor Amritanshu Prasad, who is going to speak to us about Kronecker Hecke Algebras.
So, I'm going to talk about Kronecker Hecke Algebras. And this is based on work in progress in collaboration with Raghavan here, Digjoy Paul and Jyotirmoy Ganguly. So let me just explain these words. Well, these are names of people, but let me explain what they mean in this context. So Kronecker refers to tensor products, or what are sometimes called Klebsch-Gordon coefficients. So what we are interested here are in, we have a finite group G, and the representation of this group is a homomorphism from G to the group of invertible matrices for some complex vector space V. And given two representations, you can take their tensor product. So you can talk about rho tensor sigma, and this evaluated at G will be rho G tensor sigma G, and this will be in GL of U tensor V. Now, a fundamental problem in representation theory is given a group G, classify its irreducible representations. And then once you've done that, you could try to take tensor products of those and try to see how they decompose. So, so what we do is, given two representations U and V, we take U tensor V and try to write it as a sum over irreducible representations W of, we take this tensor product and decompose it into irreducible representations. And each irreducible representation W, the number of times it occurs in the tensor product U tensor V is called a Klebsch-Gordon coefficient or a Kronecker coefficient. And I'm going to denote these by G, W, U, V. So here we are assuming all these U, V, and W are irreducible representations, and three irreducible representations determine a non-negative integer G, W, U, V. Sometimes this problem has a very nice solution. For example, if you take the group G to be the general linear group GLN over complex numbers or the unitary group, and you look only at polynomial representations in the case of GLN, or you look at continuous representations in the case of the unitary group, then the problem of classification of representations is classically solved from the work of Frobenius, Schur, and Hermann Weyl. And also the problem of determining these coefficients, it's much harder and was done much later by Lascaux and Schutzenberger, and it's called the Littlewood-Richardson rule. So G equals GLNC leads to the Littlewood-Richardson rule. Okay, but if G is the other group which was studied by Frobenius and Schur more than 100 years ago was the symmetric group. In that case, these are actually called Kronecker coefficients, and this is still doesn't have a nice answer like the Littlewood-Richardson rule, and continues to be a problem of some interest to mathematicians, physicists, and computer scientists. So this leads to Kronecker coefficients. even questions like, can you decide whether Kronecker coefficient is positive or not? These are difficult problems. Okay, so that explains the Kronecker part, and let me come to the Hecke part. So, historically, Hecke algebras are algebras where Hecke operators live. In the theory of modular forms, you come across these operators called Hecke algebras, and they actually have a nice group theoretic or interpretation which came later. But I'm be interested in a simpler finite analog of this. And so you have a group G, let's say again finite. It doesn't have to be for what I'm saying, but let's just, and a subgroup K. Now this group G, you can construct an algebra from it called the group algebra of G. It's usually denoted by C square brackets G, and one can think of it as just functions from G to C, and multiplication is defined by requiring that f star G of x is a sum over all pairs u comma v such that uv is equal to f x f of u g of u. And this gives rise to an associative algebra called the group algebra of G. And the Hecke algebra associated to G and K, usually denoted by Hg comma K, is just the subalgebra of this, which has the property that f of K1 G K2 is f of G for all K1 K2 in K and G in G. So this is just a subspace, but you can check that under this product, it actually forms a subalgebra of the group algebra. And this is called the Hecke algebra of G relative to K. If you take SL2QP for G and SL2ZP for K, then the algebra is generated by a single generator, which is a Hecke operator. But here G could be, for example, it could be any group or subgroup. And so I'll give you a specific example that we're interested in later when we construct Kronecker Hecke algebras. So what about the representation theory of this group? So the idea behind this Hecke operator is to somehow take the elements in the group algebra of G, and this invariance condition is saying that you're sort of averaging over the subgroup K. Okay, so you can think of this also as EK, CG, EK, where EK is an idempotent operator which comes from averaging over the subgroup K. And what this subgroup, this Hecke algebra captures is a part of the representation theory of the group G, the part of the representation theory which admits K invariants. So irreducible, or should I say simple, HKG modules, HGK modules, these correspond to irreducible representations of G, let's say, which I'll call V, such that V has non-zero vectors invariant under the subgroup K. Okay, so every irreducible representation of G which has a non-zero vector invariant under K gives rise to a representation of the Hecke algebra. And we have the formula, a nice, well, so this comes from the general theory of semi-simple algebras, that the dimension of this is the sum over all irreducible representations V of the group G of the dimension of the k invariants of V squared. Okay, so both, there may be other ways of computing the left hand side, and the right hand side is representation theoretic. In many cases, the left hand side is of a combinatorial nature, as we shall see in a moment. So now I want to combine these two ideas, or rather I want to apply this idea of Hecke algebras to try to understand Kronecker coefficients. So now I can define the Kronecker-Hecke algebra, and I'll denote it by Kg. And this is just the Hecke algebra where the big group is the Cartesian cube of G, and the subgroup is just the diagonal copy of G sitting inside this. So this is just G comma G comma G, where G is in G, sitting inside G cubed. And that's, well, certainly a subgroup. And that's called the Kronecker-Hecke algebra. And why is it called the Kronecker-Hecke algebra? Well, recall this fact that the irreducible representations of G, well, I'm sort of overusing now the letter G. So, yeah, but anyway, irreducible representations of G cubed which have an invariant vector under delta G will be the simple modules for this algebra Kg. So, irreducible Kg modules are irreducible representations of G cubed. So, what's an irreducible representation of G cubed? Well, it's just three irreducible representations of G tensored with each other. So, they are triples U, V, W, and what we need to know is that this tensor product U tensor V tensor W, this has a vector that's invariant under the diagonal action of G. So, let's just say non-negative. Okay, and now I'll explain the connection with Kronecker coefficients. So, U tensor V is sum over W taken G W U V times. So, G W U V, remember I had written this earlier, the same thing, is the multiplicity of W in the tensor product of U and V. Another way of thinking about this is the same as saying that G U V W is the dimension of the invariant subspace of U tensor, V tensor, the contragradient representation to W under the action of delta G. And here I am using a simple fact called Hom tensor duality, which says that the homomorphisms into something is the same as taking tensors with that, and what with its dual, and this is the so what you see is that this I can just modify this definition a little bit and write something GUVW to be defined to be GW tilde UV. And this has the advantage of becoming now more symmetric in the three arguments U, V, and W. And so GUVW is just the dimension of U tensor V tensor W under the diagonal action of G. So, so now indeed what you see is that the irreducible representations of Kg correspond to triples U, V, and W, which admit a non-zero vector that's invariant under the tensor product. And what is more, the dimension of this simple module is going to, this irreducible module is going to be precisely the Kronecker coefficient. So this, so what we get is that dimension of Kg, so earlier I had written something of the dimension of the Hecke algebra as a sum of squares, applies here, and this gives sum over U, V, W, G, W, G, U, V, W squared. Sum over all triples of representations U, V, and W of the group G. So, we were, Raghavan, Digjoy, Jyotirmoy and we were working on this, and we were particularly interested in the question of finding groups for which all Kronecker coefficients are 0 or 1, groups with multiplicity free tensor products. And we were trying to understand if we can compute. So one way of thinking about that is to say that this Kronecker-Hecke algebra should be a commutative algebra. And we were trying to characterize such groups, and we have made some partial progress. But coincidentally at that same time, Bal sent us some preprints by Ben Gelun and Ram Gopalan, who were working on exactly the same problem for symmetric groups. And they were looking at Kronecker-Hecke algebras where G is a symmetric group and trying to understand the Kronecker coefficients using that. And they in fact had this equation in that case. And in this case of symmetric groups, they used what they call ribbon graphs to parameterize this. But let me just come back to that a little more. In the general case, not just for symmetric groups. So this Hecke algebra is parameterized by G cubed mod delta G mod delta G. So the dimension of the Hecke algebra is obtained by taking the group G cubed, modding out by the left and right action of the diagonal copy of G. So if you can count the cardinality of this set, you will be able to count the dimension of the Hecke algebra. And you can kind of simplify this situation a bit, because if you have an element of G cubed, you can certainly multiply on the left or on the right by a diagonal, an element of the form G, 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 and make the first coordinate equal to 1, leaving you with only 2 coordinates. And this turns out to be the same as G squared modulo what I'll call simultaneous conjugacy. So this Hecke algebra HKG turns out to be the algebra of functions from G cross G to C such that f of Gx G inverse Gy G inverse is equal to f of xy. So the subalgebra of the group algebra of G cross G consisting of functions which are invariant under simultaneous conjugation. When you take G to be a group of matrices, this is the dreaded simultaneous similarity problem. However, you can use Burnside's lemma, for example, to compute the dimension of this thing. And in the case of symmetric groups, Ben Galoon and Ramgoolam index these by ribbon graphs. Okay, so I think my time is almost up, so I'll just end with one last result, which comes from viewing these algebras as complexifications of real dagger algebras, which are sort of real versions of C-star algebras. And in the case of symmetric group, this is slightly simpler, but let me write down the general result here. So, summation over U V W. Now, what I want, I asked Ramgoolam, do you have a formula for G U V W if I don't want the sum of squares, just the sum? And he said, yes, I do. They are in fact some of these things which are fixed by an involution. And the answer is what I call doubly, the number of doubly real conjugacy classes. So an element is said to be real if it is conjugate to its inverse. If there exists G in G such that Gx G inverse is equal to x. And a pair is said to be doubly real if there exists G in G such that Gx G inverse is x inverse. Is equal to x inverse if it's conjugate to its inverse, and Gy G inverse is equal to y inverse. Every permutation is conjugate to its inverse, but not every pair of permutations is conjugate to the inverse pair simultaneously. And this is not quite true in general, while it's true for symmetric groups. And what comes up here in general is the Frobenius-Schur indicator of these representations. Okay, so so maybe I'll just stop with that.